Hello, Internet! Last videos were about TensorFlow code implementation. Today we're going to talk about Captum. This is for model interpretability for PyTorch. So here we go. Our topic is still that we want to understand explainable AI system that show us if we can trust this system. And I found this resource here, Captum. I suppose it is by Facebook Incorporated, yes. And it is a library and now built on PyTorch. Last videos, TensorFlow, now we switch to PyTorch. And what is nice, if you have a look at this, that you have a description of the algorithms provided. And here we have 3 levels. We have the primary attribution, the layer attribution, and a single neuron attribution. And here on the right-hand side, you have, for the primary attribution, integrated gradients. This is exactly what I showed you in the video about integrated gradients programming in TensorFlow, where we went through a code example from start to finish, where we could identify the pixel in image of the human retina, where we could find some lesions. And now here you have integrated gradients as the first method, and you can see here there are a lot of other methodologies. Then you have here the layer attribution and the different code sequences and the neuron attribution. And the nice thing about this, what I really like, if you now have here a look at the main page, that if you go for integrated gradients, again, we have the formula we discussed in the last video, from the TensorFlow video. You have the original paper, where this is our ArXiv paper, which is really nice, gives you the PDF to download here. And you always have a short explanation of the methodology and the original publication where the scientist, the researcher, published their ideas. And as you can see, we have here quite a different, we have here now gradient SHAP, we have deep lift SHAP, all the different alteration and evolution of the systems. And you always have original paper, even some videos attached to the paper. So this is really nice if you're looking for some further code examples, if you're looking for a new method for augmenting your explainable AI system. I think this is a very nice description where you can find quite a lot of approaches for explainable AI. Here, for example, LIME, kernel SHAP, layer attribution. So really interesting if you want to play around, if you want to have a deep dive into this, if you want to have a short look at it, no problem at all. You have a comparison matrix. You can compare them, input-output example, feature whatsoever. But I think one of the most interesting things is also, API reference. Again, we have here our attribution, integrated gradients, again, saliency, deep lift, SHAP, whatever, layer attribution, neuron attribution, everything in detail. So you will find what you are looking for. But the nice things, I guess, are the tutorials. So you have quite a lot of code already for you to start with. And here with attribution, feature attribution, the first one is interpreting text models. And if you look here, of course, you have a GitHub repository, you have your text, and you are running a sentiment analysis. And what you want to find out, of course, PyTorch code, you have here the different cells in a Jupyter notebook. And then what you end up with more or less is positive, negative connotation. What was positive? Positive is in green. It was a fantastic. So fantastic is the course that it was labeled positive with .96. The best film ever was positive, great, positive, and then horrible, of course, bad, terrible. You see here all the different attribution levels from the different words in our most simple case. Now, I went through this and I focused that there is interpreting BERT. And there is especially interpreting BERT models. And this is what interested me. So I had a deep dive here where is it? I went to the GitHub repository, the BERT Squad Interpret notebook, and I tried to run this notebook. And I have to say, this was the first time for me. You have a question and a text, the typical BERT. Yeah? You have the question and answer series. What is important to us? This is the question, and the answer is, it is important to us to include, empower, and support humans of all kinds. Okay, so this is the problem we are facing with, and we want to know, hey, where does the answer start if we find this? And we defined, as always, a ground truth for the prediction start and end position. And here the ground truth here in this cell is defined to include, empower, and support humans of all kinds. And you can have a different ways, and I follow here the notebook they provide for it, for computing the attribution for the embedding layers. And one option is to use the layer integrated gradients. So integrated gradients, our last video, and compute the attribution with respect to the word embedding. Or the second option is to use the layer integrated gradients for the word embeddings, for the token type embeddings, and for the position embeddings. And I said, okay, I have a look. I try to follow the code of the second one. And if you look at this, the multi-embedding attribution code, I run into some problems. I would like to show you. So here we have it, the top 5 attributed embeddings for the start position. So this is now, if you apply this code, what the system comes up with. And you have now start position, and you know the start position is given our truth. Where is it? The ground truth is start position here 2 to include empower there, and the end position would be kinds of all kinds. So just a very, very simple identification. Okay, what the system comes up with, the top 5 attributed embeddings for the start position is now for our word based attribution distribution, we have here it. And it is the it because we have several commas and interpolation and everything. We have it 8. So we have the it here from the position 8. And then we have the comma from position 15. This is this one. It says, okay, here we start. No, it should be 213, but starts comma 15 or it 8. I mean, this is the beginning of the answer. And then we have important. Important is 10. And so it goes on, and you have here the top 5 attributed word embeddings. You can do the same for the token type, the attribution, and for the position attribution. And then if you look at now the verbal explanation, they tell you that the word embeddings help to focus more on the surrounding tokens of the predicted answer start position, such as M. In the word embedding, there's no M at all. Or I get it. I don't get it. Sorry. I do not understand the presentation. Then they say there's also the token M power. You know, this is BERT. So we have # power. But # power is not part of the word indexation. The top 5 attributed embeddings for words. And the comma, well, there's a comma at position 15. So I don't know. And it goes on. In contrast to word embedding, the token embedding type, so the second column here focuses more on the tokens and the text. This part is important. There's no important in the top 5. M for empower. There's M at position 4. What about position 1, 2, 3? And the start token 2. There's no start token 2 in the top 5. And the position embedding also has high attribution score for the tokens surrounding, such as us and important. Us, again, is in position number 4 from top 5, and important is not at all in the top 5. So, I think something's happening there. So I don't know if I have made a mistake, or here the text or the explanation for the code they provided, there was some misunderstanding, or I simply do not get it. Now for the end position, the top 5 attributed embeddings for the end position. Here we go. And you know that given our ground truth, the end is kinds. This is found by the word and by the position index kind. Yeah, beautiful. And you see the token type does not even have kind in the top 5. So it says the token kinds, which is the correct predicted token, appears to have a high attribution score according both with the word and the position embedding. So the word, kinds, and the position embedding. Beautiful, that's it. But then they tell you it's interesting to observe high concentration of highly attributed tokens such as off. Now, the token off is just position 4. Token off is here also position 4. Token off is here position 5. A high concentration of highly attributed token. I don't see it with off. Kinds, yeah, this is the correct answer, okay. Support. Again, highly concentrated. Support is not part in the word embeddings. I don't find it here in the token embeddings and it's not in the position embeddings, the top. And I don't know, and the same with power. For the end embeddings, power is not in the top 5, neither in word embedding, token embedding, or position embedding. So I guess I do not understand what's going on here. And you see exactly what happens is now I start, maybe emotionally, maybe wrongly, not to trust this model because the description of the model does not fit the data of this model. So I don't know what's wrong. I looked at it a second time and I still do not get it. So if you find a solution, please leave me a remark in the comments of this video. And then they start to interpreting BERT layers, which would be highly interesting. But again here, have a look at this. This is the behavior of the different layers from layer 1 to layer 12. And here again is a demonstration, sentence, question and answer. And here we have a heat map. A heat map of attributions across all layers and all tokens for the start position prediction. And I don't know. I don't know what you make out of this, but if this is our heat map and we have black is 0 and light, something light is 1, I do not get, I mean, this looks, have a look at what? Now, it starts with the layers to become more and more important. Yeah, heat map goes up, goes up, goes up, and then suddenly at layer 11, it goes half, and with layer 12, it almost goes to 0, close to 0, which is interesting. I don't know how this happens. I mean, I see that it happens, but I cannot explain how it happens. And even more interestingly, look at the token it here at the beginning of our ground truth. No, of our answer. And we have here in the layer 10, we have a solid middle ground, let's say here, and then suddenly we jump almost close to 1. This continuity here that's happening here. Why is this happening here and at this borderline, at this limes? I don't get it. I mean, you see, I see that the gradient that develops here, this sounds reasonable to me. I say, okay, this contributes, this builds up, but this, I don't know, discontinuities, I do not understand it. I think it's interesting, but why the hell is this happening? What's happening behind the scene here? And looking at the other one, you see, sometimes I find, I don't know, things I cannot explain to myself. So therefore, a very interesting methodology, but I'm not sure if I take a deep insight from this explanation about BERT. And let's have a look at this. If you want to distinguish, hey, is this orange peak according to layer 2, or is it the orange peak according to layer 12? And they have the same orange. I mean, come on, if you have such a peak and you have the same color again, I mean, I understand a 12 layer, but gee, heaven's sake, I mean, if I want to understand this, shouldn't it be possible to have a clear identification on the different layers? And so you see my point. You see the point I have here. A real interesting resource, I think, Captum, interpreting BERT models, the interpretability of these models, great job. showing all the different possibilities you have. But if you go in the nitty-gritty with BERT, I was not able to follow this. And I think it's a pity because this really sounds interesting. So if you have any idea what's going on here, where I get stuck, please leave me a comment in the remarks of this video. And I hope that you can use this resource, Captum Model Interpretability by PyTorch from Facebook, to increase the performance of your AI models and maybe switch to explainable AI systems. Thank you. This was it for today, and I see you in the next video.